Hello, and welcome to this Farrat Industrial CPD Module 1, Vibration Control of Machinery. This CPD is worth 20 credits. Let's get started. During today's introductory module, we will examine the types of vibration that affect industrial performance, the effects these forms of vibration have, and how to isolate and control them. To begin, here's an overview of the types of vibration that affect machinery. There are three principal types of vibrations that can affect mechanical equipment and machine tools. Force vibrations, self-excited vibrations or chatter, and transient vibrations, which are generated by shock. Force vibrations can be generated within the machine or external to the machine, whereas self-excited vibrations are only internal to the machine, and transient vibrations are only external to the machine. Force vibrations are defined as periodic in nature and are often generated by rotating equipment. The graph on screen demonstrates an example of periodic force vibration, described by its frequency and amplitude. The frequency is measured in hertz and is equal to 1 over t, with t being the period in seconds. Some application-based examples of force vibrations in machinery include imbalance problems from spindles, pulleys, motors, pumps or fans, which generate a frequency at the rotating speed in revolutions per second or hertz. Another example is bearing defects. There are three types of bearing defect frequencies that are caused by damage to bearing components. There are also drive belt problems, which generate a vibration at the belt pass frequency, as well as damaged gears, which generate a frequency at the shaft rotational speed times the number of teeth on the gear, or vibration due to cutter tooth impacts, which would generate a frequency at the rotating speed times the number of teeth on the cutter. As with all of these examples, the result will end in imperfections to the finished product as well as operational inefficiencies. We must also consider how force vibrations are amplified. In this example, you can see the vibration spectra measured on a motor at two different motor speeds. The dominant feature measures 63 Hz. If we reduce the motor speed, it has a significant impact on the amplitude of the vibration, increasing the motor speed by almost 5 times. What do you think caused the vibration to increase in amplitude at the lower motor speed? What we're seeing here is the effect of structural resonance. On the example, we can see that the resonance of the machine at 62.5 Hz causes amplification of the motor vibration at 63 Hz. Both frequencies are too close to each other. Three parameters govern the resonant characteristics of a structure: stiffness, mass, and damping. You can use the formula on screen to relate the frequency of resonance to mass and stiffness. The effect of damping is significant mainly at resonance. Therefore, increasing the damping reduces the response of the system resonance. As a simple guide to handling force vibration, we advise that you first identify the source of the force vibration that is causing the problem. This may be marks on the workpiece or transmission of vibrations to sensitive equipment. Then you should try to remove the source. In some cases, it may be necessary to modify the structure, in which case a modal analysis will be required. Whereas in other scenarios, it may be simply a case of mechanically isolating the problematic vibration frequency by mounting the equipment on a resilient anti-vibration mount. For the vibration isolation to be effective, the natural frequency of the isolated system must be well below the disturbing frequency. Next, we'll explore self-excited vibration, otherwise known as chatter. Self-excited vibration, or otherwise known as chatter, is described as the rapid build-up of vibration at the resonant frequency of the machine. This is commonly caused by the interaction between cut-in forces and the resonant characteristics of the structure. In terms of application-based chatter, this mainly applies to machine tools or in machines that lack stiffness and damping. In order to resist chatter excitation, you therefore require stiff machines with plenty of damping. To investigate chatter problems, we use a technique called modal analysis. When conducting modal analysis, you must first excite the machine using a shaker or an instrument hammer to identify the resonant frequency responsible for the chatter. Once identified, the problematic resonance is loaded into the modal analysis software to determine its associated deflection shape. By analysing the deflection shape, you can determine the root cause of the problem and then move towards developing a solution. A common solution to chatter is the use of tuned mass dampers, which increase damping. From the examples on screen, you can see the improvement in the work surface finish of steel or aluminium after fitting dampers to the machine. Tuned mass dampers can also be installed on roll grinding machines to improve roll quality. As demonstrated in the example here. Using a recent case example, chatter was caused by a structural weakness in the support of a wheelhead assembly. Tuned mass dampers were therefore fitted to the wheelhead to increase its damping capacity. Here you can see where the tuned mass dampers were fitted to the wheelhead. And finally, let's explore transient vibrations caused by shock. Transient vibrations are shock impulses generated outside of the machine, which can transmit and affect nearby machinery and structures. Shock impulses generated outside of a machine can affect its own vibration performance. For example, dropping a heavy load near a sensitive machine will cause vibration to transmit to the workpiece and affect its surface finish. Similarly, operating heavy machinery causes vibration to transmit outward to the building and other sensitive equipment. Under both of these circumstances, mechanical isolation is required in the form of an anti-vibration mount. Here, you can see an example of transient vibrations measured on the floor of a production facility, generated as a result of shock impulses emitted from a nearby forge. In this recent case example, anti-vibration mounts were inserted underneath the bed of a roll grinding machine to reduce the transient vibrations caused by shock. You can see on the picture where the mounts were positioned to improve the performance of the machine. Now that we have explored each type of vibration, their impact, and how the effects can be resolved, let's summarize our learnings. Force vibrations can be generated both within and external to the machine. To combat force vibrations, remove the source of the vibration. In some circumstances, you may need to mechanically isolate the problematic vibration frequency by mounting the equipment on resilient anti-vibration mounts. Self-excited chatter vibrations originate internally from the machine. Chatter usually occurs in machine tools which lack stiffness and damping. In order to resolve chatter, you will need to identify the resonant frequency responsible using tools such as modal analysis. And finally, transient vibrations originate external to the machine. Shock impulses create vibrations which emit outward and impact the machine itself, as well as surrounding structures and machinery. Mechanical isolation is required to combat this form of vibration, such as anti-vibration mounts. Congratulations! You have now reached the end of this introductory module. For more information on this subject or to discuss an engineering challenge, please do contact us. And remember, reputable manufacturers like Farrat will always be able to discuss design proposals and assist in specifying the right product for the job.